Hey physicists, going to go through an example of each of the three discussions in our momentum packet. Here, so we have momentum, a 2 kilogram block moves to the right at 4 meters per second. First, sketch that situation. Let me go ahead and put a 2 kilogram block here, and I'll have it moving to the right. Remember, direction is important, at 4 meters per second. What's the momentum of the ball? Calculate with units. Use the value P. For momentum is mass times velocity. That's going to be equal to 2 kilograms times our 4 meters per second to the right. That's going to be 8. Now these interesting units of momentum, kilogram meter per second to the right. Okay. The other way we can document that is with our momentum chart. Remember from the videos that our momentum chart has velocity in meters per second on the horizontal axis. Put 0 in the middle there. And along the horizontal axis we'll have mass in kilograms. That's a scalar quantity. So in this case, let's go ahead and we have a velocity of 4 meters per second. 1, 2, 3, 4 meters per second. And let's see, we have a mass of 2 kilograms. Okay, so we've ended up making a chart of this. Next is, what is the area of the momentum chart? Remember that area is equal to base times height. The base of this rectangle is 2 kilograms. Its height is 4. Hold on a moment there. Let me correct that. Is 4 meters per second. And this is going to be in the positive direction, so that's what we're assuming. We're assigning to right. So that is 8 kilogram meters per second is the area. You know, it's not always, let's say, square inches or whatever, but it can be whatever this unit is. Kilogram meters per second, positive indicates it's to the right. Hey, so you can go ahead and pause this video now, complete your discussion 1 packet, and in a few moments I'll take a look at discussion 2. Hey, let's take a look at impulse and changing momentum. So in this case, our impulse, a 5 kilogram bowling ball initially at rest, is pushed to the right with a net force of 4 newtons for 3 seconds. Let's go ahead and sketch that situation. So initially, got my bowling ball. We'll have a force to the right of 4 newtons. Okay, and 3 seconds later, our bowling ball is probably moving to the right. Okay, we've sketched our situation. All right. We're going to use our initial momentum chart, impulse chart, and final momentum chart to help us solve this problem. We want to keep in mind our questions here. What is the final momentum of the ball? Calculate with units. And what is the velocity of the ball after the push? Hey, so our initial momentum is going to be pretty boring here. Okay, we have velocity and mass. Remember that momentum is inertia in motion, and in this case our initial velocity is 0. You can see that from rest. So I'll just trace this out. 1, 2, 3, 4, 5 kilograms. Well, it has no height to it. Okay, so our initial momentum is equal to 0. Remember, impulse is how we give an object momentum or change its momentum. So let's go ahead and trace that. Our impulse chart has force on the vertical axis, time on the horizontal axis, and we're applying a force of 4 newtons. 1, 2, 3, 4 newtons, and we're applying that for 3 seconds. 1, 2, 3 seconds. The area of our rectangle here is our impulse, which we use the letter J, is equal to force times time, which is 4 newtons times 3 seconds. And remember, the units for these come out to be exactly the same as for momentum. So we'll get 12 kilogram meters per second. Remember that a Newton second is the same as a kilogram meter per second. So our initial momentum plus our change in momentum caused by impulse is going to be equal our final momentum. Let's go ahead and we'll trace that out. We know that our object still has 5 kilograms of mass, 1, 2, 3, 4, 5, and that the area of our rectangle here will be the momentum, and the momentum is going to be equal to our initial momentum 0 plus our change in momentum due to the impulse, 12 kilogram meters per second. And so we've answered the first question, what's the final momentum of the ball with units? That's going to be 12 kilogram meters per second, and it has direction, so to the right, the area of this. And the last thing we have to look at, hey, what's the velocity of this ball? And we know that momentum is equal to mass times velocity. We have the mass, and we have the momentum, so we can figure out what the velocity is. Another way of thinking of this is, hey, if I'm given the area of a rectangle, and I have the base, what's the height? So we could also express this as momentum divided by mass is going to be equal to our velocity. Our momentum is 12 kilogram meters per second divided by 5 kilograms equals 2.4 meters per second. So we've got to answer the second part. What's the velocity? 2.4 meters per second to the right. So we know that we're at 2.4 here. All right. Hey, so that's the second discussion. Go ahead and pause that. Finish discussion 2. In a little bit, I'll give an example for discussion 3. Hey, so welcome back. We're going to be looking at discussion 3, the conservation of momentum. And in this case, item 1, separation. We have a 2 kilogram green cart and a 2 kilogram blue cart, both at rest, with a compressed spring between them. The spring is released. The green cart and the blue cart fly apart in different directions. We can see that the green cart is given a velocity of 3 meters per second to the right. And we want to know what is the velocity with direction of the blue cart after the spring is released. Okay, so we'll use our initial momentum and final momentum charts to help us solve this problem. So I've drawn the blue cart on the left, the green cart on the right. The situation before is that the spring is all bound up and it's at rest, so we know that the initial velocity for both of them is 0. Afterward, they're going to fly apart. So after we see the green cart flying to the right at 3 meters per second, it makes sense that the blue cart would move to the left, and we'll figure out how fast that is. Spring is sprung. Okay, let's go ahead and take a look at our initial momentum charts, our final momentum charts, and then through conservation of momentum, see if we can figure out how fast this would end up going. So let's take a look at the momentum chart for the blue cart. The mass is 2 kilograms. But it has no velocity. I'll just put an X to kind of show that it's there. And our green cart, starting it here, 2 kilograms. Again, it has no velocity. So our initial velocity is equal to 0. Neither cart is moving, so there's no velocity. Because we're considering our system both carts, that's the importance of circling our things. Because we're considering our system to be both carts, there are no net external forces, so the sum of forces is equal to 0. If the sum of forces are equal to 0, that means there's no change in momentum, no impulse. So we know our final momentum is also equal to 0. Okay, that's going to be important to solve this problem. For the green cart, I'll put a little box or rectangle to indicate its momentum. So I'll start from here. I have 2 kilograms of mass, and then I'll go up. It's going 3 meters per second. So 1, 2, 3. So this rectangle here indicates the momentum of the green cart. The total momentum is going to be 0, but it doesn't mean the momentum of each object is going to be 0. Okay, and so this is at 3 meters per second. Hey, really by inspection then, I know that whatever area I have up, I'm going to have to end up compensating for with some area down, because my net momentum won't change and my initial momentum was 0. My final momentum is 0. So this is also going to have to be down 1, 2, 3 meters per second. I can do that even without much in the way of calculation. So it's negative 3 meters per second. These two areas, if you want to think about it, have to be the same area, either above and below the axis, or they have to cancel. You can think of it that way. So what is the velocity of the blue cart? We know it's 3 meters per second to the left. If we want to, we can also call that negative 3 meters per second. Okay. Conservation momentum equation. If there are no net external forces, and we know that here because anything that's interacting we've included as part of the system, we know that the initial momentum is equal to the final momentum. That's the conservation momentum equation. Now let's take a look at what makes that up. Our initial momentum is equal to, in this case, the mass of our blue cart times the velocity of the blue cart initial plus the mass of the green cart times the velocity of the green cart initial. Our final momentum is made up of the momentums of each of those. The mass of our blue cart times the velocity of our blue cart, final, plus the mass of our green cart times the velocity of our green cart, final. Let's go ahead and put numbers in this one. We already know the initial momentum was 0. Let's look at this. The mass of our blue cart was 2 kilograms. Our velocity was negative 3 meters per second, plus the mass of our green cart, 2 kilograms, times 3 meters per second. We'll have a minus 6 kilogram meters per second here, a plus 6 kilogram meters per second here. Our momentum is 0. Go ahead and finish up that other problem on momentum, and good luck.